10 years ago, I started DIY drones as a way to kind of bring open source and the maker movement to the aerospace industry, and that worked really well. Built one of the biggest robotics communities in the world, built companies, built an industry, and we kind of took over the future of the air with a kind of bottoms-up homebrew computer club model. 10 years on to the day, we think that the next domain ready to be sort of DIY'd is cars, autonomous cars. The hardware's good enough, the software's more than good enough. The use cases and the excitement about it is out there, and the problem is, once again, like the aerospace world, you could read about drones, but you couldn't have one. Now you can read about a self-driving car, but unless you're very rich, you can't have one. Well, we should make it so people can have one. And this notion of democratizing advanced technology is kind of what I do, and cars are what we do now. A great video game is easy to pick up but hard to master, and we think technology should be the same thing. So, we live in the golden age of DIY technologies. There's Raspberry Pi, there's open source, there's Arduino, and we're like, let's just start with the stuff that's already out there. It's super, like a Raspberry Pi costs like 30 bucks, the code's amazing. The communities are massive, they're taught in schools. Let's just take the stuff you already have in your home, crappy RC toy, a Raspberry Pi that is probably sitting around, some code you can download off the internet, and let's give you a sort of a full autonomous car, proper computer vision experience right now in your living room this weekend. And this is not like, a fake little exercise you do for school. This is the same technology that's used by the pros, just at larger size, at greater cost. And if you like it and you want to do more of it, the trajectory takes you right up there into, your classic Silicon Valley autonomous car startup. So with drones, we kind of avoided that as long as we could. So it's not like okay, here's a kit, here's a toy, call Boeing. The impedance match is so radically different. I mean, we were thinking in terms of, new versions every 6 weeks, and Boeing does a new version about every 16 years. And it's just like, this sort of metabolic rate, we're fast, cheap, and out of control. I mean, that's literally the logo, fast, cheap, and out of control. And it's very difficult to go into a big company with a fast, cheap, and out of control mentality. Among other things, they have liabilities, they have lawyers, they have shareholders. So, big companies, when it comes to robotics, big companies I've found have been difficult to work with. When it comes to actually using robots for, as a purpose, in our case with drones, it's with data, in a case of autonomous cars, it might be for transportation, then it gets a lot easier because you can sort of say, ignore the robot. It's a done thing. Let's talk about how to use it. And then big companies get involved. Right now we're exploring both. So we go faster all the time, and that's just sort of getting your code to move more quickly and more sensitive, etc. The nimbleness is right where we're starting. So typically it's all been time trials, one car on a track at a time, and that's all about speed. But when you put two cars on the track, wheel-to-wheel racing, then you could have the best car in the world, but if you get knocked off the track by another car, you've lost. So now you have to think about things like not just avoiding, but also tactics. So think Mario Kart. How do you win with Mario Kart? Do you win with the fastest kart, or do you win with the best tactics? Bananas, laser guns, bouncing off things, all of that stuff. So I don't know what the equivalent of banana is here, but we're going to have to do things like here's a simple thing. Inside lane, passing on the inside lane. An obvious thing, right? Any racer knows this. This is the so-called racing line through a track. That's right what we'll be doing this next week, is optimizing around the racing line on a track. Okay, so the next one is, okay, now everybody does the racing line. Now it's all getting crowded there. When do you pass? Again, a driver knows all this. Presumably you pass like coming out of a turn, or you pass before the turn, but you don't pass in the turn. Well, we need to code that. But that's a problem. It's not a super hard problem, but it's a problem that I assume that the Waymos of the world aren't doing because it's not a relevant problem for them. They definitely pass cars, so there's a safe way to do it, but they're not trying to pass a car faster than that car. That was built in from scratch, but that's what a neural network does. It's a learning algorithm. So the way it starts is at the beginning of the day. Let's say you've got a new track. At the beginning of the day, you just manually drive the car around the track a few times, and it's learning the track. So it's correlating what it sees with the actions that the steering actions. Then you gathered a lot of data, you send it up to the AWS cloud, it cranks through the convolutional neural networks and comes back with a model, which is basically a correlation table. When you see this, do that. It's not quite as simple as that, but you get the idea. And so morning was learning AI, training the AI. It's called supervised learning in this case. And afternoon is the AI runs the car. So the AI's, you think of AI as being something fancy, but it's just a Raspberry Pi and an AWS cluster.